In this video, we will be reviewing lipids, the only one of the four large biomolecules or class of biomolecules that don't actually the use of polymers. But instead, lipids are grouped in a way where they have one shared trait, the fact that they have little to no affinity for water, which makes them hydrophobic substances. And exactly why I will explain in this video. So there are three types of lipids that I want to talk about in this video: steroids, phospholipids, and fats. We will first start with fats, right? What are fats? Fats are essentially a large molecule that are composed of two smaller molecules, glycerol plus fatty acid. A glycerol is a 3-carbon, I'm going to draw it here kind of big, a 3-carbon molecule that has a hydroxyl group and hydrogen bonds, right? This is glycerol. Now, fatty acids are essentially these long carbon skeletons where one end is a carboxyl group. So its carboxyl group looks like C double bond O OH. And it's these long sort of chain of carbon and hydrogen bonds, sort of forming the skeleton here. And they can go on to be, 16, 18, 10, 20, they can get pretty long, right? And so there's no set amount here. They can go on for as long as they want. That's a fatty acid, right? The only thing that is the connection between these carbons, hydrogen, and the fact that there's a carboxyl group here, C double bond O OH. Now, if I was to combine these two molecules together, from last video, we learned a process, right, known as dehydration reaction. Now, even though we're not dealing with polymers here, we can very well use a dehydration reaction as long as we can produce a water molecule out of this. And we most certainly can. We can take the hydrogen from here and this OH group from here and take it out for it to be a H2O. And now we have just linked this carboxyl group, which is not a carboxyl group anymore, to this oxygen, right? And so let's say we were to do this, since there are three hydroxyl groups, if you were to do this 3 times, so I'm just going to simplify this here, and I'm just going to draw like a box, right? Let's just say this box represents another fatty acid. And this box represents another fatty acid, right? If I was to do this every time, 3 times, and I was to, let's say, take out the water molecule from here, combine it together, forms another H2O, forms another H2O. I'll be left with 3 of these hydroxyl groups now occupied with these fatty acids. When you have a glycerol molecule filled with 3 fatty acids connected to its hydroxyl group, that is called a triacyl glycerol. That's the resulting product. The full combination of 3 fatty acids to 1 glycerol is a triacyl glycerol. Triacyl as in 3. Next, let's talk about the different types of fatty acids you can find. There are 2, unsaturated and saturated. Now, I'm sure we have heard about this many times in nutrition labels, food labels. I hear about it in protein powders all the time, right? Unsaturated and saturated fat. What are they? We're going to go back here. Let's look at the carbon skeleton again. We have a C double bond O OH, and we have a bunch of carbons. Carbon, 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 carbon. And then we have these hydrogen, right? Now, the one thing that's similar here is that they're all single bonds, right? They're all, for the most part, single bonds, except for that one double bond at that C double O. But in terms of the skeleton, these are all single bonds. This is known as a saturated fatty acid. This is a saturated fat, and this is a saturated fatty acid. The carbons are sticking close together, and this is exactly why this becomes a solid. In particular, this can be butter. For example, saturated fat is butter. Let's look at when these carbons don't really stick that close to one another. Let's see what happens when there's a C double bond O OH, and what happens when there are carbons and then all of a sudden there's a double bond between a carbon, right? Because that can happen. That results, right? We can have a bunch of H here, H here, H here, right? We know that these exist here. That results in there being a kink. What that looks like in a space filling model is essentially we have the carboxyl group here, and we have a long chain, right? A long chain, and it ends up having a kink like this. Whereas in this saturated molecule, you have sort of like the straight structure. That is called a unsaturated fatty acid. Unsaturated fatty acid. right? There's a double bond that forms in the carbon skeleton, within the carbon skeleton, right? Because there's a double bond here outside in this carboxyl group, but we want it to only happen inside the skeleton. Once it does, then it becomes an unsaturated fatty acid. Unsaturated fatty acids now have this space, and this space at room temperature then becomes liquid. So when we look at something like, for example, like vegetable oil or something, unsaturated fatty acid, these molecules, like olive oil, for example, cannot actually stick together, and therefore these will become liquid at room temperature. That's fats. Now let's talk about steroids for a little bit, right? Steroids are a pretty simple concept, and so now let's talk about steroids, right? Steroids ultimately are lipids that are characterized by a carbon skeleton that has 4 fused rings. What does that look like? 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. And right, these are 4 fused rings that are together, and essentially it's just a difference of how you have certain groups oriented. For example, here we can have a CH3, we can have a CH3 here, and then this can expand out to a certain degree, and this can be a cholesterol, right? Cholesterol is a type of steroid, and is a very common component of animal cell membranes, and also is a precursor where other steroids are produced: testosterone, estrogen, etc., etc. And it's only the difference of the way these groups are present, but in general, almost all steroids have these 4 fused rings. That's how they're characterized. Lastly, let's talk about phospholipids, which is going to be one of the most consistent type of lipids that are going to come in later chapters, especially when you talk about the cell. Phospholipids essentially is similar to a fat, but only has 2 fatty acids attached to a glycerol rather than 3. Now, the glycerol, so for example, we have, let's just say that this component here is the glycerol. There are fatty acids here, 1 saturated, 1 unsaturated fatty acid, and phospholipid. If the title says it's a phospholipid, we know we can understand the lipid part. We have a glycerol and 2 fatty acids, but where are we getting this phospho from? The phosphate group. There needs to be a phosphate group in here for it to be considered a phospholipid, right? This is the phosphate group. And in total, we have a phospholipid. Now, let's understand why fatty acids are hydrophobic. Fatty acids are hydrophobic because the C and H bonds, right? We see these C and H bonds, right? These C and H bonds are nonpolar, right? These are nonpolar bonds. And water loves polar bonds. So what happens when these bonds are nonpolar is that the fats separate from the water, because the water molecules form hydrogen bonds between other water molecules, not these hydrogen molecules, because they are nonpolar bonds sticking close to the carbon, right? That's why if we have H2O here and H2O here, they're not going to want to interact with this because they're already in this mess, right? These water molecules are just going to want to react to other water molecules, form polar covalent bonds with one another. They're going to form hydrogen bonds to one another, they're going to form nonpolar covalent bonds to one another, and they're going to form hydrogen bonds to one another, and they're not going to want to form bonds with these nonpolar CH bonds. Therefore, fat always stays separate from water. An example of that being, vegetable oil, for example. It separates from a vinegar solution when you put it in salad dressing. And so now when we understand the fact that these C and H bonds are hydrophobic, it's safe to assume that the tail region here, this tail region, is hydrophobic. And there's nothing going on up here for this head area to be a hydrophobic region. So this head area is actually hydrophilic, right? Allows water to pass through, allows water to enter its surface, right? And usually there's another compound added here called a choline for it to form a complete complete phospholipid.